Hi everyone, Dr. Gray here. Today we are working on Universe Target 5. Our learning target today is understands the sun's gravity holds the Earth and other planets in their orbits, just as each planet's gravity keeps its moon in orbit, and understands how mass relates to gravity. And as you can see from our title here, we are going to focus on this relationship between mass and gravity here today. If you're curious and you want to know what you would weigh on different planets, this QR code will take you to a web page where you can plug in your weight and it will tell you what you would weigh on Jupiter or Saturn or the moon or any of those other places. It's just kind of a for fun piece there, so enjoy. So let's get down to the nitty-gritty. If we're talking about gravity, the first name that usually comes to mind with respect to gravity is Sir Isaac Newton. And Newton did some work in the 17th century and figured out that the relationship between the force due to gravity and the mass of the object, and also the distance between objects, is governed by this formula. And so this formula is Newton's law of universal gravitation. Now, this is a pretty complex formula, so let's look at what each of its parts mean. The first part that we have here is our F, and the F is what we're going to be calculating most of the time. F is the force between the masses. This is the gravitational force, and in fact, from now on, we're going to refer to this as F sub grav. That way we know it's the gravitational force, because there are lots of forces that we can talk about in physics. There could be electrostatic forces, there could be the force necessary to push a box up a hill. There's all kinds of forces. And so let's call this one F grav so that we know that we're talking about the gravitational force. The next part of this formula is the capital G here, and this capital G is for the gravitational constant. And the term constant, the word constant here means constant, means it doesn't change. And so when we are doing our calculations, we are not calculating G. G does not stand for gravity. It is simply the constant that we will use to do our calculations. And so let me give you those values. So I told you that G is a constant, and here I am, and I'm going to give you two values for it. And if you look closely at these two, you'll see that they're actually the exact same value. Sometimes we will use G as equal to 6.674 times 10 to the negative 11th. Its units are newtons meters squared per kilogram squared. Or sometimes we'll use it as 6.674 times 10 to the negative 17th. Newtons kilometers squared per kilogram squared. And so whether or not we use the top one here or the bottom one here depends on whether the distance between the centers of our masses, which we'll talk about in a second, are measured in meters or kilometers. But I will give you some help with that. Also know that you'll never have to memorize these constants. I will always provide the constant for you, though I imagine by the time you get done doing all these practice problems, you will have memorized it at least long enough to take the test. All right, so moving right along, our next variable in our formula is m sub 1. Now, well, actually we have m sub 1 and m sub 2. When we talk about gravity, gravity is a force of attraction between any two objects with mass. And so m1 is the mass of the first object. The 1 is to represent object 1, m stands for mass. m2 is going to be the mass of the second object. The last variable in our formula here is r, and r stands for the distance between the centers of the two masses. And this value is squared. Now, before we get into plugging numbers into this formula, and we will do lots of that, let's just talk about this formula in a qualitative way. So we're not going to do quantitative, we're not going to not use quantities, but we're just going to talk about what would happen in a conceptual sort of way. So if we look at this formula here, what we find is that the masses are on top of our formula here, or are on the top part of our equation. And if we were to plug in values for those masses, we're going to have to multiply those masses times our gravitational constant. Well, what this means, because our force, our gravitational force here, and our masses are both essentially on top of the fraction, right? Because we could write this F as just F over 1. Because both the force, the F, and the M's are on the top half of our fraction, that means that the gravitational force varies directly with the mass of the objects. If the mass of the object increases, or objects, because we have two objects here, then the gravitational force also increases. Now, if we look at our formula again and look at r here, notice that r is on the bottom of our fraction. And that means that gravitational force varies indirectly with the distance between the two objects. In other words, if the distance between objects increases, then the force between them decreases. And so we see if one goes up, the other one goes down. This is an indirect variation. Sometimes we say that the two values are inversely proportional. In fact, the relationship between force and distance between the objects is governed by what we refer to as an inverse square law. Because this r value is squared, hence the squared part of the inverse square, what that means is that the distance between the two objects has more of an impact on the gravitational force between those two objects than the mass of those two objects themselves. Now, what this allows us to do is just to make some qualitative predictions about what the relative forces between two objects are going to be. For instance, if we have two objects and our objects are, let's say we have a banana and a gorilla. Well, if that gorilla is holding on to that banana, they're going to be close together. And so there's going to be some force of attraction between the gorilla and the gorilla's banana. Now, if we take that banana and separate it from that gorilla, now the distance between the gorilla and that banana is much greater, the gravitational force is going to go down. If we were to swap out that banana with a bicycle, well, now the mass of that bicycle is much greater than the mass of the banana, and so the force of attraction between the gorilla and the bicycle is going to be greater than the force of attraction between the banana and the. So let's try this with another qualitative example. If you are halfway between the Earth and the Moon, would you get pulled to the Earth, the Moon, or stay where you are? Well, in order to figure this out, what we would have to think about is, well, is the gravitational force between you and the Earth greater or less than the gravitational force between you and the Moon? Well, if we start thinking about our values here, so we've got two things that we want to calculate. We want to calculate the force between me and Earth, and we want to calculate the force between me and the Moon. Well, in order to calculate the force between me and the Earth, I would need to know the mass of me. So my mass, we're going to say it's just 50 kilograms. You may use 50 kilograms as your mass. It's a pretty good mass for a high school student. If you want to know what your exact mass in kilograms is, you can Google your weight. You would just put in, like, my weight is 135 pounds. You could just Google 135 pounds equals kilograms, and Google will tell you exactly what you weigh in kilograms. But you can use 50 kilograms for any time I ask for your mass or my mass or a classmate's mass. The next thing that we're going to need is the mass of the Moon. Now, the mass of the Earth, because we're looking for the force of attraction between me and the Earth. And so the mass of the Earth is huge. It is 5.97 times 10 to the 24th kilograms. We're going to call that 6 times 10 to the 24th kilograms. Let's just make it easy. We'll just round it. And then we've got the distance between. Well, we're going to come back to that in just a second. Since we're just going to do a qualitative comparison of these two, We don't really need to know that value, and I'll explain why in just a second. Now let's go look at some values for the force of attraction between me and the moon. Well, my mass for the second equation over here is still going to be the same. Mass 1, or my mass, is still 50 kilograms. And now the mass 2, which is now the mass of the moon, is going to be much, much less. It's about 1/6 of the mass of the Earth. And so 1/6 of that is going to be 1 times 10 to the 24th kilograms. Still way more than me, but a lot less than the Earth itself. Now, let's talk about this R. If we have, here's Earth, here's the moon, and here's me hanging out in the spacesuit in between. Well, if we look back at our problem, it says you are halfway between the Earth and the moon. Well, that means that the distance between the Earth and me, floating in space, is the same as the distance between me and the moon as I float in space. And so really it doesn't matter what our R values are going to be here. Because if we're going to just compare these two values, well, the gravitational constant, our G, in this formula is going to be the same for both calculations, so we can ignore it. And our R's are the same in this formula, and so we can ignore that too. Because whether we plug in, whatever values we plug in for G and R, it's going to be the same in both calculations. And so when you do a qualitative comparison, you can just leave those out because ultimately they're going to kind of cancel out in both occasions. What we have to really look at is which of these variables is different. Well, my mass, whether we're looking at the relationship between me and the sun, me and the Earth, or me and the moon, that doesn't change. The only thing that changes is the mass of that second object. The mass of the Earth is 6 times greater than the mass of the moon, which means that the force due to gravity between me and the Earth is going to be 6 times greater than the force of attraction between me and the moon. And that's without ever having to know what the distance between those two objects are. That's a qualitative comparison. And we would expect that. You would expect to be pulled to the Earth, or pulled back to the Earth if you were halfway between. In order to get pulled to the moon, you would have to be much, much closer to the moon in order to get pulled that direction. All right, so now let's put some actual numbers in this formula. Let's play with this formula some. We want to calculate the force of attraction between you and your closest neighbor. Assume you are sitting a distance of 1 meter apart. Well, we want to calculate the force, so force is our unknown. In order to calculate our force, we're going to use Newton's universal law of gravitation. G is given down here. G is 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. You're going to need the force of U, the mass of U. And so I'm just going to use 50 kilograms here because I don't know who's paying attention. I don't know who's listening today. So we're going to assume you weigh about 50 kilograms. And we're also going to assume that your neighbor has a mass of 50 kilograms as well. So we have our M1 and our M2. And we are sitting a distance of 1 meter apart. So that means that R equals 1 meter. And so if we plug our values into, or if we plug our values into this formula, force is going to be equal to our G, which is 6.674. And I'm going to, instead of writing times 10 to the negative 11th, I'm going to introduce you to a new notation. This is E negative 11. Makes the much easier to write this all in. And our units are newtons meters squared per kilogram squared. It's always important to follow your units. Mass 1 is 50 kilograms. Mass 2 is 50 kilograms. I just lost my G, but it's there. And R, well, we have 1 meter and 1 meter. And that's the way we get R squared, is R squared is just R times R. And so for the sake of plugging this into our calculator, I'm going to do it this way. I think it will be the easiest for everybody to understand. And so before we plug in our numbers into our calculator, we want to check units. We have kilograms times kilograms are going to be kilograms squared. Well, kilograms squared are going to factor out kilograms squared there. Meters times meters will factor out meters squared here. And the only unit we'll have left is newtons, which is perfect because newtons are the unit that measure force. And so we're going to end up with an answer in newtons. To do our calculation, we're going to make use of this button. If you're using one of my calculators in my classroom, this is known as the scientific notation key, what I refer to as the EE button. If you're using your own scientific calculator, it might be EXP. On some calculators, it's just an E. On some calculators, it is 10 raised to the X power. But for our purposes, I'm just going to call this the EE button. Now, if we go back to the values in our formula, we have 6.674 EE negative 11 times 50 times 50 divided by 1 divided by 1 equals, and notice it's going to give you back that answer, give you your answer back using scientific notation. This is going to be 1.6685 EE negative 7, or this would be 1.66 times 10 to the negative 7th. So the answer to our question, the force of attraction between you and your neighbor, which is sitting 1 meter away from you, is 1.67 times 10 to the negative 7th newtons. It's important we don't forget to include the units in our answer. So now let's look at what happens when the distance between you and your neighbor changes from 1 meter, which is what it was in the previous problem, to now being 1,000 meters apart. So we're still calculating F. We want F grav is what we want to find. Our mass 1, my mass, is still 50 kilograms. The mass of my neighbor, mass 2, is still 50 kilograms. Except now the distance, or R, is going to be 1,000 meters. And so if we plug those into our formula, we have F equals G, 6.674 E negative 11 Newton meters squared per kilogram squared, times mass 1, 50 kilograms, mass 2, 50 kilograms, got my G that time, divided by R. So R now is 1,000 meters. We're going to do that twice, so we have that R value squared. So we take out our calculator and enter 6.674 EE negative 11 times 50 times 50 divided by 1,000 divided by 1,000. It is important to divide by both of those 1,000s in this case, unless you want to use parentheses here. But it really is just easy to divide by both of those numbers. And this equals 1.6685 EE negative 13. So the answer to our question now is that the force between me and my neighbor, now that we're 1,000 meters apart, is 1.67 times 10 to the negative 13 newtons. So how did increasing the distance between you and your neighbor affect the gravitational pull between you? Well, let's look at that. Let's compare how the force of attraction between you and your neighbor has changed as the distance between you has increased. The force between you and your neighbor when we were 1 meter apart was 1.67 times 10 to the negative 7 newtons. And the force when you were 1,000 meters apart was 1.67 times 10 to the negative 13 newtons. And this number has a smaller negative exponent, so this one is not quite as small a value as that other value. So we're going to put that value on top. We're going to, in order to compare these two, we're going to just divide the two by each other. And so what we end up with is that the ratio between these two values, if we divide 1.67 times 10 to the negative 7th by 1.67 times 10 to the negative 13, is 1 million. So when you're 1 meter from your neighbor, the force of attraction between you is 1 million times stronger than if you're 1,000 meters apart. And what this really shows us, this 1 million is actually equal to 1,000 squared. And that 1,000 was that distance that we increased between you and your neighbor. And so we can see that the force of gravitational attraction between any two masses decreases, just as we would expect, as the distance between them increases. There's that indirect variation. So let's look at the last kind of problem you're going to work with in this target. Here we have, compare the gravitational force you feel on Earth to the gravitational force you would feel on the International Space Station. And so again here we have this compare, which means we're going to need two values that we're going to have to find the ratio of. We need to know the force, the gravitational force on Earth, and we need to know the gravitational force on the International Space Station. Well, the mass of the Earth is the biggest mass in this area, and so it's going to be the object that creates the gravitational pull. And so we're still going to need the mass of the Earth. Mass of the Earth was 6 times 10, or just e to the 24 kilograms. The mass of me, we're going to leave that at 50 kilograms. Now, the r in this value, if we go back and we look at this, it is the distance between the centers of the masses. Now, this is an important thing to think about, because we're not looking at the distance between the two masses. We're looking at the distance between the centers of the two masses. And because of the size of the Earth, that is a huge value. If you're standing on the Earth, you're this little teeny tiny person standing on the Earth, we're going to go from your center, so from your center to the Earth's center. What we need to know is how far is it to the center of the Earth. What we really need to know is what's the radius of the Earth. Well, the radius of the Earth is 6,371 kilometers. And because our distance now is in kilometers instead of meters, we're going to use that other value for g. G is going to be 6.674 EE negative 17 newtons kilometers squared per kilogram. Now, when we want to look at these values for the force of attraction between you and the Earth when you're on the International Space Station, well, the mass of the Earth hasn't changed. That's the same. The mass of you, that doesn't change either. What changes is the distance between you and the Earth. And so now, we're going to put you, let's see, we'll put you out here, now, or put me out here. Now, and this is obviously not to scale, but now we still have to go from my center to the center of the planet, and so we still have the radius of the Earth here. So this is the radius of the Earth, and we're going to have to add to that the distance between you and the Earth. And so we're going to have to add 250 kilometers to that radial value, to the radius of the Earth, because that's about how far away the International Space Station is. The radius here is going to be 6,371 kilometers plus 250 kilometers, so that our total distance now is 6,621 kilometers, 6,621 kilometers. And so we're going to find our two force values, just like we did in the previous problem where we were looking at the force of attraction between you and your neighbor, and then we're going to find the ratio between those two. So let's set up our calculations. First, let's calculate the force between you and the center of the Earth. So that's our force from the Earth. So we have G. We're still using Newton's universal law of gravitation as our formula. G is now 6.674 E negative 17 newtons kilometers squared per kilogram squared. Then we need mass 1. Well, we can make that mass of the Earth, so that's 6e24 kilograms. And mass 2, that's my mass, that's the just 50 kilograms. I feel pretty puny next to the Earth. And now we're going to divide that by our R value. And so if we're looking for the force from when we're standing on the Earth, we're just using the radius of the Earth. And so we have 6,371 kilometers. 6,371 kilometers. Check our units, kilometers times kilometers, factors kilometers squared, kilograms times kilograms, factors kilograms squared. So we'll be left with units of just newtons. We take out our calculator, 6.674 EE negative 17 this time, make sure you use the right value, times 6EE24 times 50 divided by 6371 divided by 6371 equals, now the force is 493 and change. So the answer to our question, the force between you when you're standing on the surface of the Earth, is 493 newtons. So that's the force standing on the Earth. Now, the question isn't what's the force standing on the Earth. The question is compare the force if you're standing or if you're floating in space next to the International Space Station. Well, if we go back to our formula, if we want the force due to the International Space Station, the gravitational constant is the same. The mass of the Earth is the same. The mass of you is the same. The only thing that's different now is we're going to use this value. We're going to use 6,621 kilometers to do our calculation.
So 6.674 EE negative 17 times 6EE24 times 50 divided by 6621 divided by 6621 equals, now the force, we've moved further away, we expect the force to go down, and now it's 456.7 newtons.
So the force, when you're next to the International Space Station, will make that 457 newtons. So let's find the ratio between those two values. We're going to just divide 493 by 457. And our ratio, FE, or force on the Earth, to the force by the International Space Station. The force on the Earth is 1.08 times stronger than the force of attraction if you're floating out there next to the International Space Station. It's always, because the Earth is on top, that tells us that it's the force of attraction between the Earth is greater than the force of attraction to the International Space Station. That's it for today. I'll see you in class.